Welcome to 64th lecture. We are studying circuit analysis and we are studying three-phase systems. Today we'll study power in three-phase system. Before this, we have already studied that for a single-phase system, we have three types of powers: the average power or active power, P, the reactive power Q, and the complex power S. Today we'll study all these three power expressions for all these three types of power for a three-phase system. Right. To begin with, let's start with the per phase representation. In a single in each phase of a three-phase system, the power would be the phase voltage times the time times the phase current times the cosecant of the angle between the voltage and current. The units are watts. It's equivalent to the power in a single phase system, right? And Q is can be written on the same lines: V sub P times I sub P times sine of theta. Whereas this subscript P and this subscript P, they refer to the phase quantities, whereas this represent to per phase, right? So this is P per phase. So P V phase times I phase times cosecant of theta, and for Q this is V phase times I phase times sine of theta, right? So for a Y connected system, let's see what this quantity is, and this both P and Q for a Y connected system. We already know that for a Y connected system we have the per phase representation like this. We have this voltage as per phase, which we can also write as, we know that we have two types of voltages in Y, the line voltage and the phase voltage, and phase voltage can be written as square VL divided by square root of 3, line voltage divided by square root of 3. Whereas we have only one current, we have already studied, we have only one type of current in Y system, that is IP or IL, right? So IP can be written as IL, whereas VP, the phase voltage, is VL over square root of 3. So the per phase representation can also be, the per phase power can also be represented in the form of line voltage and line current for a Y connected system. And for a Y connected system, the same reactive power can be written as, except that we have sine of theta instead of cosecant of theta here, right? So now we have, up till now we have written power in a single phase of a three-phase system in terms of the phase quantities Vp and Ip, and the line quantities VL and IL for Y connected system. For even for delta connected system, these two expressions remain the same. Let's see how. To start with, we'll start from the same point, that per phase power is V phase times I phase times cosecant of theta. The same point where we started this lecture. V phase I phase times cosecant of theta. So in a delta connected system, we have this V phase is equal to V line, because we know that in a delta connected system we have only one kind or one type of voltage, whereas we have two types of voltages. The current here is the line current, whereas current in one phase is the phase current. So phase current can be written as the line current divided by square root of 3. So putting Ip is equal to IL square root of 3 divided by square root of 3, and Vp as VL, we reach the same point, the same expression that we reached to in case of Y connected system. So for Y and delta, no matter we are using Y or delta, we have the same expressions for per phase active and reactive powers. So for active, the expressions for active and reactive power are the same, no matter we are using Y-connected system, or we are using the delta connected system, right? So what should be the total power then? It's very simple. The total power should be 3 times the per phase power. And we have studied the expressions for per phase power, P and QP, P sub P and Q sub P in terms of phase and line quantities. So per phase power is 3 times, total power is 3 times the per phase power. So one of the expressions for per phase power is in terms of line voltages. If you put it here, we reach to these two expressions. That in terms of line quantities, VL and IL, total power can be written as square root of 3 times VL times IL times cosecant of theta. And QT can also be written in terms of line quantities like this. So, or in other words, the total power can also be written in terms of phase quantities. So if we have phase quantities or line quantities, if we have line quantities, we'll use these two expressions. And if we have phase quantities, Vp and Ip, we'll use these two expressions. So now we have in total, we have four expressions for power. If we have line quantities and we have to calculate average and reactive power, we'll use these two expressions. And if we have phase quantities, we'll use these two expressions, right? And finally, the complex power, we already know that total complex power, even for a single phase, the complex power is the average power plus minus J, the reactive power, right? So even for three phase, the total complex power would be the total average power plus minus J times the total reactive power. So this is a complex number, and this complex number, this is the rectangular form of this complex number. The same complex number can also be written in terms of its polar quantities. So the magnitude of ST, the total power, can be written as square root of P squared plus Q squared, right? So in terms of polar quantities, this can be written as the magnitude R is this, and the angle theta would be the inverse tan of y over x. In this case, Q total divided by P total. So using these simple expressions, we can compute average power, reactive power, and complex power for a three-phase system. In our upcoming lecture, we'll solve a numerical problem related to these three types of power. Thank you.